All right, graphing logs. Let me give you a second to try. See what you remember about graphing logs. So what it is, I gave you a basic setup, both for exponential and log. Maybe I'll put them both up again. So for exponential, it goes like that. It hits up here at A, and the equation is y equals b to the x plus A. Oh, no, that's not A. Sorry. Wait, let me try again. What's A in the exponential equation? Yeah, the horizontal asymptote. Hey, Wendy's here with us for our last visit. So A is the horizontal asymptote. So good to have that right on your sheet. And then log graphs, remember what log graphs do? They have a vertical, because they're the opposite, right? Exponential log, we got that theme a million times, right? Exponentials and logs are opposites. What is a logarithm? The inverse function of an exponential. So they have a vertical. No surprise if exponentials have a horizontal asymptote. Logs have a vertical asymptote. Remember what the equation is? Y equals log base b of x. So this is at A. This is here at A. What's the equation? X. Good job. Remember, it's opposite because, anything next. We always learn that anything next to X is always opposite, huh? No surprise. So the vertical asymptote is at positive A. It's the opposite, isn't it? And so where's the log graph? It's here. Let me put it like this. Goes like that, and it takes a dive at the vertical, doesn't it? So it goes up, but it goes up slow growth. That's a slow growth one. Concave down, like a bowl turned down. Concave down. You talk more about concavity. It's the second derivative in calculus. We'll talk about concavity. And then exponentials, fast growth, bowl turned up, concave up. And there it is. So there's the basic. Good to have that. Put that right now on your final exam prep sheet for, logs and exponentials. There we go. So a lot of the battle, what'll help you in the battle is identifying the direction. Notice that all the graphs initially go up to the right, don't they? This one goes up to the right. This one goes up to all of them. All the ones I've given you start out by going up to the right. So then if they're not going up, if the one you're looking at, like this one, well, this one does go up to the right, doesn't it? So that means there's no negatives anywhere, right? At least remember, if we have a negative on the front, that makes any graph go down. If you have a negative on X, that makes any graph go left. But our graph is going up and to the right. So that's positive in the front, positive on X. You good with that direction thing? So that's what eliminate most of the things right away. And then you just do the table after that. So you get the hang of that? That's how we learn to do the graphing thing. We would get the direction and eliminate most of the options right away by whether it should have positive or negative in the front and positive or negative on X. And then you come down to like one or maybe two options, then make a table. Remember that game plan for doing graphs? So again, it's all about if there's negative in the front, that's down. Let me lay that out one more time. Maybe it'd be best just to put it, I'll just put it here. If there's negative in the front, if there's positive in the front, that's up. All right? Positive in the front is up. And then positive on X is to the right. Negative on X is to the left. So front tells you up or down. The sign on the front's up or down. Sign on the X is right or left. So, and then just look at your graph. What do we have on our graph? We have it's going up and to the right, which means we want positive in the front and positive on X. So could option A be right? No. What's wrong with A? Negative. Got a negative in the front of the log. No way. How about option B?
No, negative in X.
Negative in the front of the X? No way. How about option C?
Yes.
Maybe. How about option D?
Yes.
Maybe. They're both maybes, and of course there's always the E. So, all right, so we got A and B out of there. We're down to C and D. You understand the difference between C and D, right? On D, that -2 is not in the toaster, so to speak. It's not plugged into the log function. It's outside of the log function, isn't it? It's a Y effector on D. And on C, that -2 is an X effector. He's in there in X's world having a right-left effect, an opposite. Remember, X is always opposite. So he's going to have a right-to effect. Anyway, what did we learn about the asymptote lines? Let's look at that now. Whatever's in there with X, opposite plus A, right, tells you where the vertical is. So could C be the right answer?
No.
That would mean a +2 vertical. An asymptote would have to be right there at +2, wouldn't it? And it's clearly not. The log graph is not taking a dive at +2. Where's he taking a dive? Right on 0. Right? You can't see it. He kind of blends into the axis. He gets so close. But see him right here? He's taking a dive right there, isn't he? Right at X is 0. Which means there's what? Nothing in the argument with X, which is good with D. D's looking good so far. We'll do a table to make sure. But I'd bet my money on D at this point. Right? See why D's good? D's got all the plus minus stuff right. D's got the vertical asymptote right. Right? You with me? There's on D, it's Y equals log. There's nothing. I'll put parentheses. Maybe that'll make it more clear. That's really what D is saying. That -2 on D is not in there with X, right? Which means there's really what? Nothing in there with X. 0, which means that's where the vertical should be. And indeed, our graph does have a vertical asymptote right at 0. That's all lining up, isn't it? Does that make sense? So you see the crucial difference between C and D? It's all about whether you're in there with X or not in there with X. And if you're in there with X, that determines your vertical asymptote. We have one at 0, so we need nothing in there with X. D's looking good. You can double check. How about I just move on? Well, maybe I'll do it real quick here. It just moves the graph down 2, which is a little deceiving because the graph goes up forever. So it's kind of funny to, I mean, it slides it down 2, but it's hard to see it because it goes up forever. So if you slide something down 2 that's going up forever, it's hard to see it. So it does slide it down 2, though. So I would just make a table. What do we always plug into the table when we're testing to see if something's right? Remember how we find the center. This will really help you. Make sure you got this down. How do you find the center point?
0.
Make X's world 0. X's world. What's in there with X? Plug in whatever it takes to make X's world 0. That's where you'll find the center. So what do I plug in?
0.
Just 0. In this case, 0. Right? You know what I mean? If that had log of X minus 7 minus 2, I'd plug in 7, for example. Right? You plug in whatever makes X's little world 0. That's always where the central point will be located. Okay, so you plug that in. So you take log 0 minus. You can hit the buttons on your calculator. What are you going to get? Do you know already? What's log of 0? Don't reach for those calculators. You should know this one. Yeah, no, it's a no-go. It's an error. You can't put 0 or negative into logs, remember? No zeros or negatives into logs. So they're outside the domain. So no way on that, 0 or negative. And then, so now what do we do for our next point? Add 1, plug in a 1, log of 1. You can use your calculator. It'll be 0, 0 minus 2, negative 2. So the only point I've actually got is over 1 down 2. Is the point over 1 down 2 on the graph? Over 1 down 2. Beautiful. Look at that. There it is. Yeah, for sure he's our answer. D it is. Good on that? Remember all that kind of stuff? Very good. Questions I can answer? So we've got to make both bases become a plane 3. How can you make 1/3? Here, I'll just rewrite it here. How can you make 1/3 become plane 3? 3 to what power is 1/3? Good job. You remember that? Yeah, negative powers. Flip things, huh? -1 is 1/3. 3 to the -1 is 1/3. That's right. The other side, you guys know, 9, that's just 3 squared. Good so far? So I made both, yeah. So remember, we make the bases the same. And now, we can just set the powers equal, huh? Meaning minus 1 times 5x plus 6 must equal 2 times x minus 2. Why do the powers have to be equal? Because the bases are the same. Right? Once you've made the bases the same, if 3 to something is equaling 3 to something else, those powers must be equal, because if they were different, then 3 to one of them wouldn't equal 3 to the other, would it? Once the bases are made the same, logically the powers have to be the same, or how would 3 to one of them equal 3 to the other if the powers were different? Right? Awesome.
How would the 1/3 become just a single 3 because of the negative 1 to the power?
Right. So 3 to the negative 1 power is 1/3.
Okay.
Yeah, so negative powers flip things. Yeah, so that 1/3 becomes 3 to the negative 1. All right, so now we distribute minus 5x minus 6, distribute 2x minus 4. How do we solve for x here? Just get rid of one of them, minus 2x from both. Well, we got minus 7x minus 6 is minus 4. Kind of running out of room there. Yeah, I'll just bring it up here. So minus 7x minus 6 is 4. Add the 6 to both sides. Minus 7x is 10. Divide by minus 7. There it is. Minus 10 sevenths.
Negative 4.
What did I do? Oh, it's negative 4. Thank you. So that would be 2 over minus 7. It's still none of the above. I still would have got it right, huh? See, none of the above is helping you out. See that? Maybe you don't always feel that way. Thank you. So I missed that. I lost that little negative. Don't lose your negatives. I was just trying to demonstrate how easy it is to lose negative signs. Make them big and bold, so you don't lose them like I just did. So none of the above. We good there? All right. So let's grab that down. All right, good. And so whatever makes the denominator equal 0 is vertical asymptote. Because remember, a vertical asymptote, maybe this can sink in. This is what happened for me in math science classes. First time, I would kind of memorize things, sort of monkey see, monkey do, just surviving, you know. But when I studied for the final, a lot of times, a second look, a little more time to stand back and go, oh. So maybe that'll happen for you. That's why it happened for me a lot. So remember what vertical asymptotes are? They're where the thing goes up to infinity or down to negative infinity. What makes that happen? The bottom of a fraction goes to 0. That's sinking a little deeper now, so you don't have to just monkey see, monkey do and look at steps, but you really get it. It'll help you in calculus. I could do limits. Things are going to go up and down, and if you really get that, it'll really help you in calculus. Do you get the idea? If you divide by 0, that's infinity. Do you feel that first off? Mm-hmm. Right? How many times does 0 go into 7? Forever. Right? So when the bottom goes to 0, that makes the overall thing go to infinity. That's why you have a vertical asymptote line there. That's why the graphs go up or down forever, because the denominator has become 0 or gotten infinitely close to 0. That's what you look at. That's right off the bat. Math 5A. Limits. And they'll let the bottom sometimes go to 0, sometimes the top, sometimes other things. And when the bottom heads to 0, the overall fraction, up to infinity it goes. Or down to negative infinity. So if you just know that, you'll just know what to do right away. So the bottom 0, whatever makes the bottom 0 is going to be a vertical asymptote on the graph. And so how do you solve that? You know, just bump that thing over. X squared is 3. Square root it. But roof on the house? Don't forget plus or minus, because there are going to be 2 of these. Plus or minus. Now, what's root 3? It's like 1.7, whatever. Something like that. So, right, now you might say, well, I don't have a calculator. How are we going to? Well, you know the square root of 3 is somewhere between the square root of 1 and the square root of 4. Square root of 1 is 1. Square root of 4 is 2. So you know the square root of 3 has got to be somewhere between 1 and 2. So it's 1 point something. Good enough. Am I going too quick? Did you track? Do you understand that? Square root of 1 is 1. Square root of 4 is 2. Square root of 3 has got to be between them. It's got to be 1 point something. It's 1.7. Just if you're going into STEM, it's a good idea just to know square root of 3 is 1.7. Square root of 2 is 1.414. Comes up all the time. All right, anyway, so it's 1.7. So we're looking for a graph that has vertical asymptotes at plus and minus. So here's 1, here's 2. Here's -1, -2. At plus and minus 1.7, there should be vertical asymptotes. Now, do we see that anywhere? Where do we see that?
C and D.
Yes, C and D. We don't actually see the vertical dotted lines, but you see their effects, huh? We see that the graph is going up forever and down forever. We see the effects on the graph. Right? So clearly on C and D, those it's either C or D now. We good so far?
Or E.
Oh, yeah, or no, there's no E on this one.
So it's
Even though there's an E over there, it's just a sucker option. Don't grab it. There's no E option being shown to us. So, all right, so it's C or D. C or D. Now, which one is it?
when the top part comes in play. If you want to use the top part, you can factor, right?
Yeah, so that was the vertical asymptotes. Now how do we find the horizontal asymptotes? Do you remember that? So vertical asymptotes are denominator 0. Horizontal asymptotes are a little more tricky. Now, I'll give you the table again. Horizontal asymptotes. So it's all about the numerator power. So if the how's it go? If the denominator power is greater than the numerator power, it's y equals 0. Horizontal. If the denominator equals the numerator, it's y equals a over b horizontal. If the numerator is greater than the denominator by only 1, it's a diagonal, what we called oblique. And you have to long divide. Remember those? Long divide the denom into the numerator and get the mx plus b answer. It's like a diagonal line. And then case 4, if the numerator is greater than the denominator by 2 or more, there's no horizontal, no diagonal asymptote. So those were the 4 cases for determining horizontal or diagonal. That handles horizontal and diagonal. Horizontal and diagonal asymptotes. So now that's okay. That's okay to have that table, but I encourage you, if you're going to go further in math and science, to keep thinking on that, and I'm sure some of you are already there, to where you just sense it. You're not just imitating steps, you really understand where that comes from. Why is that true? It's about limits. The first thing you're going to do in calculus. It's a horizontal asymptote is about what happens to the graph way off to the right forever or left. Right? As you go way off to the right forever, if I have an equation like x, what do I have here? X squared minus 6x plus 9. X squared minus 6x plus 9. X squared minus 3, is that what it is? Yeah. And I'm gonna let x go to infinity. I'm gonna go out like to 10,000, 10 million, 10 billion, 100 trillion, right? Way off to the right. I'm gonna go way off to the right. You're plugging in huge numbers. What's gonna happen there? Well, do you realize these two guys are gonna dominate the scene? You're plugging in like 10,000. 10,000 squared. 10,000 times 10,000 is so much bigger than just 6 times 10,000, right? 10,000 squared is 10,000 10,000s. That's a lot bigger than 6 10,000s. And, right? So all that matters in the end is the most powerful term on the top and the most powerful term on the bottom if you're going off to the right forever, which is what we're thinking about with horizontal asymptotes, huh? That's where all these things come from, is from that logic. The logic is better than the steps, always, in math and science. So what does that equal? That's just 1. That's what we mean by step 2. We're step 2. Denominator power and numerator power are tied. The tug of war, they tie, right? The top's tried to pull the function up. But is that what you were going to say, Whitney?
What I do is I divide all the things by x squared.
Yeah. Yeah, that's the formal method. I'm a little more casual. Yeah, that's what they show formally in calculus. Yeah, and that'll work too. Yeah, so I just found it's easier for students just to look at it and just grab highest, top, and bottom. So so x squared over x squared is 1. So y equals x squared over x squared. That's what a over b means. Coefficient here, coefficient there. 1 over 1, 1. So y equals 1 has got to be the horizontal asymptote, doesn't it? So let's go back. Which one of these has a horizontal asymptote at y equals positive 1? Yeah, D. See it there? Right there, horizontal. This one's at negative 1. That's wrong. So the answer is D. Good with that? Got all these steps down. Be on you. And help. 5 plus 3 ln x equals 12. So how do we solve for x there? First step, subtract 5. And then we get 3 ln x is 7. Next step, divide by the 3. So we get ln x is 7/3. Last step to get x alone. How do we get rid of that ln x? Do we divide by the ln? No, this is just like the other thing where cosine we don't divide by, right? We do the inverse function. That's because that's a function. That's ln of x. It's like a toaster. X is plugged into the function. So how do you get rid of a function? You do the opposite function, which in this case is e. That's what we learned, that logs are inverses of exponentials, aren't they? Then these cancel. E to the 7/3. There it is. Want to try number 15? Same thing, just the other way, huh? 15, you want to get rid of that e? All right, so e to the x plus 8 is 4. So what do we do to get rid of that e? We don't divide by it. We do the inverse function. Getting the hang of this? Do a lot of this in calculus, inverse function. So ln both sides, boom. So x plus 8 is ln of 4. That 4 is plugged into the natural log toaster, so to speak. Subtract the 8, ln 4. And that 8 is outside of the log function. There it is, ln 4 minus 8. That's easy. All right, how about number 16? Remember how to do 2 loggers?
Have the same base, you can and then switch it over.
Yep, count down the logs, right? Get the logs on the same side, then 2 logs, 1 log, no log. See what you remember. Give you. Okay, so for logs, okay, let me just write down. So the 2 logs plan is step 1, get the logs on the same side. So, in fact, why don't I just write it out there? Log base 3 of x plus 2. Oops, I have room there. Equals 2 plus log base 3 of x minus 3. Okay, get the logs on the same side. So just jump this log over, so it'll be log base 3 of x plus 2 minus log base 3 of x plus 3 is 2. Get them on the same side.
X minus 3.
Oh, yeah, thank you. Thank you. I'm already messing up again. Minus 3. And then step 2.
Simplify them so you log base 3 x plus 2 divided by x.
Yeah, make it into 1 log. Yeah, by the properties, remember? Adding becomes multiply, subtraction becomes divide. Yeah, there's subtraction in the middle there. Remember an easy job for 2 logs? Remember that whole analogy with the log properties? So, like if you have a big heavy table to lift, if you have a lot of people working on it, it's not hard to lift. If you just have one person, it's really hard. That's how the logs work, right? 2 logs, it's an easy job. Adding, subtracting are what I mean by the easy job. The easy operations. First things you ever did in math, adding, subtracting, right? If you have 2 logs, it's an easy operation, just adding, subtracting. For 1 log, if you make that into 1 log, it'll be harder. It'll be multiplying or dividing. Remember how that works? So this will be dividing, like that. And then step 3, how do you get rid of that log now? Cancel the log by base powering. Yeah. Whatever the base is, in this case the base is 3, do that on both sides and it cancels that out. Because remember, logs are the inverses of exponentials, of powers, aren't they? They're the inverses of powers. So when we do that on both sides, it cancels it out. So here we are again. See how we're just always doing the inverse function to get rid of a function? See that theme? So what does that leave us then? That leaves us with x plus 2 over x minus 3 is 3 squared, 9. So now we just solve that thing. How are we going to solve that thing? Cross multiply, right? I'll go to a fresh screen if you're good with that one. So we have x plus 2 over x, is it plus 3 or was it minus 3? Minus 3, yeah. And so, yeah, now just put this over 1, diagonal, diagonal. So 1 times x plus 2 is 9 times x minus 3. Distribute x plus 2, distribute 9x minus 27. So subtract 9x from both sides. Or you could have just subtracted x, whatever. Minus 8x plus 2 is minus 27. Subtract 2. So minus 8x is minus 29. Last step, divide by minus 8. So x is 29. It's positive, right? 2 negatives make positive. 29/8, maybe. Remember, you have to check these, right? Remember, all log problems. So the kind of thing I did, when I would get a final in my hand, I would look through real quick, and any problem that begins with a log that has an equal sign, like this one, see it's log with equal sign, I'd put a C next to it. To remind myself when I got to that problem, I need to check the answer. It's easy to forget that. You have to check logs. My kids, when I tell them things like that, they always think, Dad, you were just crazy. You were just too obsessed with all that. I'm like, you want good grades? That's what you do. Don't cry to me about, oh, that teacher made this too hard. My kids, I'm always like, you make your choices. You want to just flounder in there all lazy and just hope for the best. The best won't happen. But if you want to go in there intentional, if you care, if it's important to you, you can do things like this. So we got to check. So how are we going to check that answer?
Plug it in.
And plug it in. Yeah. Now what? Now it's not a hard check. It's super easy. That's why if you just remember it, it's gravy. You got it. 29/8. What is that? That's a number. That's 3 point something, isn't it? 8 goes into 29 more than 3 times, doesn't it? Mm-hmm. So that's 3 point something, okay? Remember, all we're checking is that the inside of a log is not negative or 0. Remember, that's all we don't have to work the whole thing out. Just the inside's not 0 or negative. So if you put in a number that's over 3, right? More than 3. 3 plus 2, that's fine, that's fine. More than 3 here, more than 3, 3 point whatever, 2 or whatever, minus 3, that's not going to be negative or 0, huh? So that's a good answer. It's acceptable. 29/8. There it is. 29/8. Yeah, Raymond.
Are we going to have calculators on the final?
Part, right? Part 1, no calculator. Part 2, calculator.
There's just going to be a point where...
Yeah, so anything I gave you before with no calculator, same thing on the final. It's exactly the same.
No scientific as well.
Right. Just like the last 2 exams, none at all. Part 1 and then part 2, graphing. Yep. All right. We good with that one? All right. So what do we do when we have x in the power zone on both sides?
Jump up to the front.
First we do ln,
L1 first, then jump.
and then that's what'll cause it to jump down to the front. Right? So it's the opposite again, isn't it? Inverse function. What's the opposite of x in the power zone? Logs. That's why they made logs, huh? So we ln both sides. So I'm just trying to help you remember. There's a lot to remember on the final, isn't there? So exponentials are the inverse of logs, or logs are the inverse of exponentials. So when you see powers, you think, what's the opposite of that? Logs. All right. Okay, and so now those powers drop down to the front, don't they? That was log property 3, if you remember those log properties. So x minus 2, ln 17. So a lot of people remember that much, go to there, but it's still a little tricky even from here. Now what are we going to do next? Yeah, distribute through those parentheses. Boom, boom. So you get x ln 17 minus 2 ln 17. Everybody good there? So I just, that ln 17 just multiplied both those. Now what? Yeah, good. Remember how to handle it. We've had it a few times. You'll definitely have it in calculus a lot. When you have an equation and the x that you're trying to solve for is in 2 spots. Remember what you do? You get those 2 on the same side. Factor out. So when x is in 2 spots, you, number 1, get the x's on the same side. Step 2, factor out x. Right? So jump this over. And so we'll have x ln 3 minus x ln 17 is minus 2 ln 17. And then factor out that x. Yeah, and then we'll divide. Last step, divide. Ln 3 minus ln 17. Boom. There it is. Now, on the multiple choice, I wouldn't want you to get tricked at the very end. I just grabbed the publisher's answer things, and sometimes they'll write them different. Remember how else that answer could look and still be the same, and you should grab it? It's the same as positive 2 in ln 17 over ln 17 minus ln 3. In fact, that's probably how they would write it, because they just like positive in the front there. Would you recognize that as the same? Do you see that? Let me help with that a little bit. How do we know that's really the same? Well, they basically, so whenever you get an answer, like you say you got this answer, and then you look at the multiple choice, and none of them look the same, before you grab that none of the above, stop for a second and try to multiply top and bottom by -1. Right? If you multiply top and bottom by -1, that'll make it look different without being different. So if you multiply by -1 on the top and -1 on the bottom, then negative times negative on the top becomes that positive. And what happens on the bottom? Well, that's a negative ln 3 and a positive ln 17, which is the same as this. Remember, order doesn't matter. Signs in front matter. Remember that principle? They can rearrange things all day long. It makes no difference at all as long as all the pieces have the same sign in the front of them. Order doesn't matter. You know that for like numbers, right? Think about -2 plus 3 or 3 minus 2. See, it's a -2 in both cases. It's a positive 3 in both cases. And the answer in both cases is 1. Makes no difference, huh? Order doesn't matter. Signs in front matter. Right? So that's why I'm saying minus ln 3 minus ln 3 plus ln 17 plus ln 17. That's the same answer, isn't it? They just multiplied top and bottom by -1 and then reordered the bottom. It's the same.
Or you can do it on test.
I'm not trying to trick you thinking, I'm going to rearrange these. I'll never get it. I want you to get it. It's just the publisher answers just happen that way. I'm just grabbing them off the website, people that wrote the book. And I'm just grabbing them. What it is when they did the X thing, they happened to bring the X's to the right instead of the left. See, if you move this over, that'd be positive. That's all they did. They didn't do a trick at the end. They just solved the X the other way, so it came out looking different. So I'm wanting to help you recognize. I'd be a bummer if you came down to here and did good work all the way to there and didn't recognize the answer. So try multiplying top and bottom by -1 to see. Good? Feel like you get that then? Always good to draw these things, isn't it? It's always helpful. So let's draw it. So which way is this? Well, let's just find the points first. So over 1 up 7 and over 1 up 5. I don't have room for that. I'm going to have to move this down. Okay, so let's do that. So I'll move it way down here. So over 1 up 1, 2, 3, 4, 5, 6, 7 right there. So, and right there. So here's 7, 6, 5, 4, 3, 2, 1. So over 1. So over 1 up 7, there's the vertex, and over 1 up 5, there's the focus point. Okay, so it's always good to put them on a graph. It's helpful, even though we don't have to graph on this one. It still helps us find the equation. So which way does the thing? Well, which way does the thing go? Open up, down, right, or left? Yeah, because it's the center is the vertex, and it always goes towards the focus is inside. Remember that? How the focus is always inside, like a satellite dish kind of thing, has the receiver inside. So yeah, so it's going like that. Now, you want to have on your final exam preparation sheet the 4 different directions. Remember I gave you those? And I said, if a parabola goes to the right or to the left, I gave you equations for all those different kind, or up or down. And then I gave you something to help you remember. Remember, what determines the direction is always the first power letter on the right side. So if it's going to the right, plus x, that means it's plus 4ax on the right side. If it's going to the left, negative x, that means it's minus 4ax on the right side. If it's going up, positive y direction, that means it's positive 4ay on the right side. And if it's going down, minus y, that means it's minus 4ay on the right side. The other side is just the other letter. So x squared, or no, I'm sorry, y squared, y squared, y squared, x squared, x squared. Okay, so like that. And so which one do we have? We have it down. So down is this, so it's this equation, x squared minus 4ay. So this is a good thing to have right on your full sheeted notes for the final.
And you can automatically cross some of them out.
So it's x squared equals minus 4ay, yeah. So we're talking x squared is minus 4ay. Yeah, we can probably eliminate a bunch. Now, what is the a? How do we find the a? Yeah, it's the distance from the center to the focus. Remember, that's what a is. How far from this? That's a right there. How far from the center to the focus? What's a? It's got to be 2. So this becomes x squared equals minus 4 times 2. This a is 2 times y. X squared is minus 8y. Oh, no, that's wrong. and then one other thing. So I look at the end. It's good to have those multiple choice answers. And what am I forgetting? Hey, but let me show you. See how they all have this stuff? What am I missing? The adjustment for the center, right? So everything I did would be true if that was at 0, 0. I mean, it's all good so far. I don't need to back up or anything. I just need to toss on the fact that the center is not 0, 0. It's 1, 7. Remember how that works? Opposite, opposite. So this would be x minus 1 squared and y minus 7. Right? So that's the real deal. X minus 1 squared equals what? 8 minus 8. So it's D, isn't it? There it is, D. Are we good on that? You remember that?